Question 9. A beam of monochromatic light passes through a small opening and has a power output of P. The beam has a uniform cross-sectional area A. The light is then adjusted so that its frequency remains the same, but the amplitude of the light waves becomes twice its original value, and the cross-sectional area of the beam becomes 1/4 of its original value. Which expression gives the power of the modified beam in terms of P? This question tests our understanding of the relationship between light intensity, amplitude, and the cross-sectional area of a beam. What do we know? The intensity of light is defined as the power transmitted per unit cross-sectional area of the beam, so intensity equals power divided by area. We also know that the intensity of a light wave is proportional to the square of its amplitude. This means that if the amplitude increases, the intensity increases according to the square of that change. Now let's get into the solution of the problem. Following the definition of intensity, intensity equals power divided by area. Rearranging this gives power equals intensity multiplied by area. Next, we recall the relationship between intensity and amplitude. Intensity is proportional to the square of the amplitude. Substituting the proportionality into the power relation tells us that power is proportional to the square of the amplitude multiplied by the cross-sectional area. Now we compare the modified beam with the original beam. The ratio of the new power to the original power can be written as P' divided by P equals the new amplitude squared multiplied by the new area, divided by the original amplitude squared multiplied by the original area. Now we substitute the changes given in the question. The new amplitude is twice the original amplitude, so small a' equals 2 small a. The new cross-sectional area is 1/4 of the original area. Substituting these values gives P' divided by P equals 2 small a squared multiplied by 1/4 big A, divided by small a squared multiplied by big A. First, we simplify the square. 2 small a squared equals 4 small a squared. So the expression becomes 4 small a squared multiplied by 1/4 big A, divided by small a squared big A. 4 multiplied by 1/4 equals 1. So the numerator becomes small a squared big A. This is the same as the denominator, which is also small a squared big A. Therefore, the ratio equals 1. So P' divided by P equals 1. This means the power of the modified beam is equal to the original power. Therefore, P' equals P. This is our final answer. What did we do? We started with the definition of intensity and rearranged it to express power in terms of intensity and area. Then we used the relationship between intensity and the square of the amplitude to express power in terms of amplitude and area. After substituting the changes in amplitude and beam area, we simplified the ratio and found that the two effects cancel each other. Here are a few misconceptions to watch out for, to avoid errors and problems of this kind. A common mistake in this type of problem is to assume that power is directly proportional to amplitude instead of the square of the amplitude. Another mistake is to ignore the effect of the change in cross-sectional area when comparing the two beams. Now to conclude, let's recap everything we have seen from this problem. We have seen that the intensity of a wave is proportional to the square of its amplitude. The total power carried by a wave equals the intensity multiplied by the cross-sectional area through which it passes. Reducing the cross-sectional area for the same intensity decreases the total power. When both amplitude and area change, both effects must be considered when determining the new power.